energy you can think of as the currency of nature. In real life, if you can store up a currency, you can transfer it between parties and then transform it for goods and services. That's why money is useful. So if you think about it, a $20 bill, okay, does it have any value in and of itself? Like if you're on a desert island, like you're on an airplane that crashed, would a $20 bill help you very much? Maybe to start a fire, you're right, or toilet paper, I don't know. Well, that's kind of nasty, sorry. But the idea is, in America, this only has value because we assign it value as currency. The government will back it up. And in the old days, you could actually even turn it in for gold until we went off the gold standard, whatever, right? You learn it APUS or econ or whatever. So for example, okay, money you can store up in a bank. You could store it in a check, a certificate of deposit, in some ways like on a credit card, okay? But the real idea is you can transfer it and transform it between parties. So in the old days, before we had money, for example, we might have Farmer Nick, and he wants to get some bread or something like that. So he goes to Baker Lucy and he trades some cabbage for bread. And then Farmer Colin trades a cow for bread or whatever. But after a while, it's annoying to always carry around bread and cabbage and cows. So then you go to a currency system. That's all, okay? So this thing is valuable only because we assign it value as our system of currency. So if I wanted to get some Gatorade or whatever, I could say, hey, Matt, I'll give you this for your Gatorade. And you're like, you're an idiot. Sure. Okay. So in other words, you can transfer money between parties and transform it for goods and services. So energy is nature's way to store up, transfer, and transform different forms of energy to get things done. Okay? Specifically, there are 5 main types of energy we're going to look at. And in our unit, we're going to focus on this first one. Okay? So these are 5 general categories. You might see slightly different versions in different textbooks or online, but you could really kind of break it into these 5 categories. The first one's called mechanical energy. And this is what we're going to focus on in our study here. Mechanical energy is energy of motion and forces. There are 3 main forms we'll break down in a second. It's called work energy, kinetic energy, and potential energy. And actually, if you think about it, the classic bowling ball of death demonstration, that's what we were looking at. We looked at lifting the bowling ball by doing work on it, which is a force applied over a distance. We stored that up as potential energy, which is energy by virtue of an object's position. We lifted it against the Earth's gravitational field. And then, when we released the ball, the energy was transformed from potential into kinetic energy, energy of motion. And we saw that very dramatically, that in any given system, the total energy stays constant. So that's why all of our volunteers were perfectly safe. Nobody lost any teeth, broke their nose, etc. Okay? Now, mechanical energy can be transformed between its 3 main forms, but also into any of these other forms. So the other forms of energy include heat or thermal energy, which is when you take an atom and you get it moving, then we can quantify that as heat energy there. Okay? So if you remember from chemistry, what's the difference between the molecular model for room temperature water and boiling water? The water molecules start simply doing what when you start to heat them up? They start to move faster, okay? So a little classic demonstration of heat energy is if you ever take your 2 hands, you put them together, and you start to rub, right? And after a while, what does the friction between your hands cause? Actually, it gets so hot, it's actually really uncomfortable. So a fun way to see this, and there's already a couple around the room, I'll pass out more, is I have these liquid crystals in these little plastic sheets here. You put your hand on there, and the liquid crystals will absorb that thermal energy from your hand, and it'll change the crystalline structure and reflect light off in different frequencies there, right? So then as you heat up the liquid crystals, you'll see reds and blues and greens and all that. In the 70s and 80s, this was very popular. You get like those mood rings or necklaces, things like that, okay? And then what's fun is you could like look at your, coffee breath. No, you can look at heat from your breath. You put it on the lab table. The lab table is a pretty good conductor of heat. It'll draw away, it'll cool it off, etc. Okay? Chemical energy, okay? In chemistry, a big topic was looking at chemical reactions. And really, there's 2 main types. You have your exothermic versus endothermic reactions. And all it is when an atom bonds, there's covalent, ionic, all that good stuff there. It either releases energy, absorbs energy, okay? And when you break or form bonds, you can release that energy, absorb it. Electromagnetic energy is all of modern life. We look at this next quarter there, where you can take an electric charge and you move it. So you flick a switch, you push a button, and all of modern life is trying to harness electromagnetic energy for our convenience there. Nuclear energy, and everyone's always scared of, where you split an atomic nuclei. That's called fission, like you split a uranium atom, versus fusion, where you squish them together, usually helium, hydrogen. But actually, nuclear energy isn't necessarily good or bad, okay? Just everyone gets scared because they think of what when they think of nuclear energy? Like bombs and things like that, right? But really, it's just part of nature. In fact, if there was no nuclear energy, we'd all be dead. We wouldn't be here. Because what's that big thing in the sky that keeps us warm and alive? The sun, right? The sun's a natural nuclear reactor in the sky. And in fact, you can actually think of the sun's thermonuclear reaction, as a source of all energy for everything on Earth. So even though in America we rely on fossil fuels, we're burning coal and oil. Well, how do you get coal and oil? It's because of the nuclear energy from the sun. Over time, the heat and light, as it decays plants and dinosaur bones and whatever, that's how you get your coal and oil. Okay, so ultimately, even like wind is from the sun. As you heat up ocean currents and the air, everything is from the sun ultimately there. Okay, so let's look at a couple demonstrations of energy here at the front. Okay, so most toys. Let me grab a couple toys here. There we go. Okay, that's the whole point of putting this all together. So anyway, in terms of mechanical energy, there are three main forms we're going to look at here. Okay. Money, there we go. We store it in forms of cash, checks, credit cards, etc. Energy we can break down into three main types. Work energy, the ability to put a force over a distance. Potential energy, which is energy by virtue of an object's position. And then kinetic energy, which is energy of motion there. Okay? And most sports, toys, etc., it's just looking at how do you get energy from one form to another. For cars, it's a huge problem because right now we're not relying on springs and stuff like that. We're relying on burning gasoline, right? And there's been crazy ideas like try to use compressed air, things like that. But really, probably for us, what will get us to the next step is electric cars, where you have a very good battery technology. And since we already have an electric grid, if we can upgrade that and charge up those batteries efficiently, then we can get our kinetic energy, right, to get our cars to move. And the hybrid cars are really cool. So, for example, the Toyota Prius there, what's kind of neat about that is a lot of a car's energy is wasted when you what? When you have to stop. How annoying, right? What's with that? Red light's not. But if you think about it, it takes a lot of energy to get your car moving to like 30 miles an hour or whatever, right? And every time you stop, you're wasting all that energy. So on most of the hybrid cars, when you brake, there's actually a flywheel in there that as you step on the brake, it spins a flywheel. It actually charges up the battery. So you try to recapture a lot of that energy, which is really smart. Okay? So the future is how do you get energy from one form to another as efficiently as possible? In terms of our unit, we're going to focus on these three main forms of mechanical energy. So let's go ahead and break down how these all work here. Okay? First, work energy. Work has a very specific definition. So right now, you guys really aren't doing any work, though it feels like you're doing a lot of work coming to school here. And that's because you're doing a mental workout, but not a physical workout. Okay? Work we define as a product of an applied force that you put over a distance. So notice that if you don't exert a force, no work is done. If you don't take that force and put it over a distance, then also no work is done. So if you recall, this past winter, we had this crazy thing called Snowmageddon. That was crazy, right? Anyone have to help like shovel the driveway? That was like insane, right? So a couple of my neighbors were really smart. There was some neighborhood kids who came around, like perfect, right? Great opportunity to make money. Like, hey, like $50, we'll do your driveway. Like totally good deal, right? So I was stupid. I just tried to do it all myself, okay? But I had a little snowblower and shovel and all that. Now I was trying to help some neighbors and all. But anyway, if you think about it, if you want to shovel a driveway that has like 6 feet of snow or whatever, it's a lot of work because it takes a lot of force over a lot of distance to move all that snow, okay? So a snowblower kind of makes your life easier because you got a machine that can exert a lot of force and then throw that snow like 30 feet to save you time there, right? The units is 1 Newton of force exerted over 1 meter would give you a Newton meter of work. But to make that more convenient, we call it a joule, which is a measure of energy named after James Prescott Joule, Scottish engineer, who did studies on heat transfer in engines and all that. So in honor of him, we name it the unit of energy after him. You're not used to joules, you're used to this thing, okay, called a calorie, right? Where do you see calories used all the time? For food, right, on a food wrapper. But what that is that's actually what's called a kilocalorie. A calorie with a capital C is a food calorie, which is 1,000 heat calories. 1 heat calorie will raise 1 gram of water, which is 1 cubic centimeter, 1 degree Celsius. That's actually the definition there, yeah? And that's about 4.18 joules, 4 joules. So if you see that a joule is only like a fourth of a calorie, and a calorie is just a little tiny bit of heat to raise a sugar cube of water at 1 degree Celsius. So a joule is actually a very small unit of energy. It's just a good way to picture it, okay? One year I had a student say, Mr. Lau, a joule's like a butterfly farting. And I'm like, sure. Like, I didn't know butterflies farted. That's kind of weird. But if that helps you visualize it, cool. That's kind of bizarre there, okay? So anyway, in terms of work energy, okay, notice you have to have a force put over a distance here, okay? So there's 2 tricky things when it comes to work we got to be careful of. And they are as follows, okay? The first is the direction of the force. If you put a net force on an object at an angle, you'll move it. Let's say we're going to push this cart along or whatever, right? However, if you push at an angle, notice that we could break this up into an x and y component. The x component is what actually moves this cart along, okay? The y component is only pushing down. So in this case, that's not going to move the cart. So the y component's not doing anything. You're just pushing it down. Or think of like, when you get in a car, right? If you pile more passengers into the car, you're increasing the weight, but you're not really pushing the car along. So if Scooby-Doo and Shaggy, who's definitely smoking something he shouldn't be, and let's say Scrappy-Doo get in there, you're just increasing the weight of the car, okay? So that's not really helping. But if they get out of the car and they push it along, then you're actually doing work to get it moving. So in this case, it's only the x component that does work. If this angle theta is the adjacent side to this x component, then fx is equal to f times the cosine of theta times the distance. That will be then the way you can quantify the work that's actually done to move the cart there. Okay? So the first thing that's tricky when you calculate work is only the direction of force along that motion is what does work there. Okay? So a little quick demonstration of this thing moving here is positive versus negative work. What does that mean? Okay? If you put force over distance in the same direction, then you have what's called positive work. Okay? What's that mean? Great example is your car. Okay? What does your car do? What's the job of your car mainly? It's to get you from what? Point A to point B, right? And how does the car work? It burns, for most people, gasoline. It takes chemical energy, converts it into heat or thermal energy as you combust the gasoline, and then you turn it into work and kinetic energy. Okay? Your pistons move, drives your transmission, tires can spin and push on the ground, but in the end you want kinetic energy, right? So when your car speeds up, that's considered positive work because the force, the net acceleration in the distance is to speed up your car. However, when you come to a stoplight, what do you have to do to your car? You have to actually get rid of that kinetic energy, right? You have to step on the brake. So that's usually considered negative work because you put force opposite the direction of travel, right? So your force and distance of travel are in opposite directions. So you end up decreasing the net mechanical energy of the system, and a lot of that energy is usually wasted to what? When you step on a brake. Anyone know what happens? When you step on your brakes, the brake pads squeeze the rims, right, in your car there, and what happens? Squeeze the spinning, if you have a disc brake or drum brake, whatever, right? And in the end, it's all wasted to what? To heat, right? Okay, so if we can recapture a lot of energy, that's good. Now, if force and distance are at right angles, okay, then you don't consider that any work being done because you're not in the direction of motion there, okay? So that's the tricky thing about when it comes to work there. So, in a nutshell, we were trying to summarize the main types of energy, and specifically mechanical energy is what we're going to focus in on this unit, and work is where it all starts. That's what it's all about there.